Hi, welcome to the next video. So we're going to start chapter 7 now. So, chapter 7. So chapter 7 is on applications of integration. So it's on applications of integration. Okay. So 7.1 is titled Areas Between Curves. Okay. So here we're going to use integrals to find areas of the regions that lie between the graphs of two functions. So for instance, if you have the x-axis here and the y-axis here, and you have a function f of x here, y equals f of x here, and you have a function y equals g of x here, then you have x equals a here, and you have x equals b here. Then you can talk about the region between these two curves. That is between x equals a and x equals b. Okay? We'll call this region S. So consider the region S. So consider the region S that lies between y equals f of x, y equals g of x, and between x equals a and x equals b, where f and g are continuous. Okay, and f of x is greater or equal to g of x for all x in the finite closed interval a comma b. Okay, so S is the region that lies between y equals f of x and y equals g of x, and x equals a and x equals g. That's the equal sign there. Okay, where f and g are continuous, and f of x is greater or equal to g of x for all x in finite closed interval a comma b. Okay, so we can divide this region. So where would I do that? So let's see. So I'm going to try and see if there's room here. So let's make another picture here. So I'm going to take this region and I'm going to divide it into, this is x equals a, that's x equals b. Okay. And so I'm going to divide S into n strips of equal width and approximate the ith strip by a rectangle based delta x in height. Okay, so let's say we separate this into n subintervals. Okay, so then in each subinterval, I'm going to choose a random point x sub I star, and now you're going to take this approximating rectangle. Okay, so on each subinterval, delta x, you're going to take the height of the rectangle. So the height of this rectangle is f of x sub I star minus g of x sub I star. Okay, and the width is just delta x. And so the area of that approximating rectangle is f of x sub I star minus g of x sub I star times delta x. Okay? And so you add up the areas of these n approximating rectangles, and you're approximating the area between those curves from x equals a to x equals b. So that's x equals a, that's x equals b. Okay, and so explaining that over here, you have the sum from I equals 1 to n of f of x sub I star minus g of x sub I star delta x, which is equal to the sum from I equals 1 to n of f of x sub I minus g of x sub I delta x. And so what does that mean? That means that the arbitrary point I choose in each subinterval, I choose the right endpoint. And so if each point I choose is the right endpoint of each subinterval, then you have f of x sub I minus g of x sub I. If that's the right endpoint, then x sub I star is x sub I. Okay? And so these are this times delta x is the area of each approximating rectangle. You add up the areas of those n approximating rectangles, and you approximate the area of S. Okay? And so this approximation, approximates S, the area of S. And so as n gets larger, this approximation gets better and better. And so therefore, the area A, which is the actual area of S, is equal to the limit as n approaches infinity of that sum. The sum from I equals 1 to n of f of x sub I minus g of x sub I delta x. Okay? Okay, so we get that the actual area is equal to that limit. Go. Okay, so we have that the area is that, but since the area is that, we can have this definition. The area capital A of the region bounded by the curves y equals f of x, y equals g of x, x equals a, and x equals b, where f and g are continuous, where f, g continuous, and f of x greater or equal to g of x for all x in the finite closed interval A, comma b, is capital A, which is equal to definite integral from a to b of f of x minus g of x dx. Okay, so the area A of the region bounded by the curves y equals f of x, y equals g of x equals a, and x equals b, where f, g are continuous, and f of x greater than g of x for all x in the interval a, comma b, is that. Okay, so I'll draw the same picture again. You have the x-axis, you have the y-axis. You have the interval from x equals a to x equals b. You have a continuous function f. You have a continuous function g. So this is y equals f of x. And y equals g of x are both continuous functions on the finite closed interval A, comma b. And f of x, the height of f of x is greater than equal to the height of g of x at every x for every x in the interval. And so now the region A is the area of the region between them. So the area of that shaded region is capital A. And capital A is equal to definite integral from a to b of f of x, the top function, minus g of x, the bottom function, dx. Okay, so what you need to remember is this equation. Okay, the area capital A of that shaded region is that definite integral, right? And meeting all the conditions of that definition. You get that from that. Okay? You can interpret this as limit as that definite interval. Okay, so also the area A is equal to the area under y equals f of x minus the area under y equals g of x. And so why is that? because if you took this region, right, if you want the area A, capital A of the shaded region, you could take the area above y equals f of x, right? But you would be including this, and you don't want to include it. But then when you subtract the area under g of x, you'd be subtracting the extra part you added, and you'd be left with just this region. And so capital A is that minus that. And so what this tells you is that the definite integral from a to b of f of x minus g of x dx, or if you just know this, the area under y equals f of x is from a to b of f of x dx minus the area under y equals g of x integral from a to b of g of x dx. So this definite integral is this one minus that one. Okay? And you get that from that equation. Okay, so now here we have a means of calculating the area of the region between two continuous curves on a finite closed interval. Okay, so we're going to use this equation to calculate areas of different regions. Okay, so I'll give you a moment to copy stuff down. Okay, let's keep going. So next example, find the area of the region bounded by bounded above by y equals e to the x, bounded below by y equals x, and bounded on the sides. BDD is my abbreviation for bounded. Bounded on the sides by x equals 0 and x equals 1. Okay, so we want to find the area of that region. So the solution, let's draw a picture just to illustrate it. Once you get used to these kinds of problems, you may not need to even draw the picture, but it is a good idea to draw it if you can't visualize it, or at least when you first start. So it's bounded above, the region is bounded above by y equals e to the x. And so let's draw y equals e to the x here. And we're going from x equals 0 to x equals 1. So that's y equals e to the x starting at 0 and going to the right. Then you have y equals x. And y equals x looks like that. That's y equals x. Okay? And that's bounded below. And it's bounded on the sides by x equals 0 and x equals 1. And so the region, we want to find the area of that shaded region right there. Okay, so capital A is going to represent the area of that shaded region. And by the equation we wrote before, this is definition from 0 to 1 of the top function, e to the x, minus the bottom function, x dx. And so capital A, the area of that shaded region in the picture, is equal to the value of that definite integral. And so you just compute this definite integral, and that's the answer, what the area is of that region. Okay, so an antiderivative of e to the x minus x is e to the x minus x squared over 2. That's an antiderivative of e to the x minus x. And so you evaluate it from 0 to 1. And so that's equal to e to the 1 minus 1 squared over 2 minus e to the 0 minus 0 squared over 2. So then this is equal to e minus 1/2 minus 1 minus 0, which is minus 1. So this is e minus 3/2. Okay, so the A, capital A, the area of that shaded region is e minus 3/2, which is about 1.2. Okay. So that's the solution to that example. That's it, we're done. I'll put a box at the end of the example. Okay. Good. Okay, let's do another example. Okay, so next example, define the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. Okay, so find the area of the region enclosed by the two parabolas y equals x squared and y equals 2x minus x squared. So let's do solution. Okay. So I want to find the area enclosed by those two parabolas. So let's draw a picture. Let's draw these two parabolas. So y equals x squared looks like that. Okay, that's y equals x squared. And then y equals 2x minus x squared looks like that. Okay, so y equals 2x minus x squared looks like that. And they intersect at 2 points, 0, 0. When x is 0, the y is 0 for both of them. And when x is 1, 1 squared is 1, and 2 times 1 minus 1 squared is 1. They intersect at 0, 0 and 1, 1. Okay, and so we want to find the area of the region enclosed by those two parabolas. So we want to find the area of that region right there. So let's call capital A the area of that shaded region. And so that's a definite interval from x equals 0 to x equals 1 of the top function, x squared, minus the bottom function, 2x. Oh, sorry. The top function is actually, you have to keep track of this. This is the top function, 2x minus x squared. And minus the bottom function, which is actually x squared here. Okay, so that's the top function minus the bottom function, the x. And so that's equal to definite interval from 0 to 1 of 2x minus x squared, so it's minus 2x squared dx. And that's equal to, now what's an antiderivative of the integrand function? It's x squared minus 2x cubed over 3. Okay, and you take that and you evaluate from 0 to 1. And so that's equal to 1 squared minus 2/3 times 1 cubed minus 0 squared minus 2/3 times 0 cubed. And so that's equal to 1 minus 2/3 minus 0. That's equal to 1/3. That's the final answer. Okay? Okay, so that's capital A, that's the area of the shaded region. So you draw the picture, you draw the two graphs, you find their intersection points. And so the x values, the smaller x value is the lower limit, the larger x value is the upper limit of the integral. And then it's 2x minus x squared, that's the top function, minus the bottom function, which is x squared dx. And you calculate the definite interval, 1/3, and you're done. Okay? If you're not sure where the intersection points are, you can set these two y's equal to each other. So x squared, so if you set y1 equal to y2, where that's y1, that's y2, then you get x squared is equal to 2x minus x squared. And then you solve for x. So if I add x squared to both sides, you get 2x squared, and then subtract the 2x. You get 2x squared minus 2x is 0. Factor out the greatest common factor, which is 2x. So 2x times x minus 1 is equal to 0. And the product of two real numbers is 0 when one of them is 0. So either 2x is 0 or x minus 1 is 0. That means either x is 0 or x minus 1 is 0, which means x equals 1. And so the two x values where these two graphs intersect are x equals 0 or x equals 1. When x is 0, you get y is 0. And when x is 1, you get y is 1. And so the 2 points of intersection are 0, 0 and 1, 1. Okay? So that's how you find the intersection points of those two graphs if you don't see where they are. Okay? All right. And you calculate the integral. That's it. Okay, so that's that example. Let's continue. Okay, so now let's draw another picture. And so here, we're going to look at a different time extension function. So let's say we look at this and we look at that. Okay, let's say this is y equals d, this is y equals c, that horizontal line and that horizontal line. Now let's look at this region here. Okay, and now let's look at this curve, and this is going to be x equals f of y, and this is going to be x equals g of y. This curve is x equals g of y, that's x equals f of y. And so now x is a function of y. So the input is y, the input is the y value, and the output is the x value. Okay? So in this picture, this is what this is depicting, is if a region is bounded by the curves, the continuous, let me just put the curves x equals f of y, x equals g of y, y equals c, and y equals d, where f and g are continuous. Where f, g are continuous. And f of y is greater or equal to g of y. For c less or equal to y less or equal to d. Then its area is capital A is equal to definite integral from c to d of f of y minus g of y dy. Okay? So the area of that region is that definite integral capital A. Okay? If you were to look at the approximating rectangles for the area, they would look like this. Here's the x-axis, there's the y-axis. This is, I'm going to try and draw the same g here, and the same f. X equals f of y, x equals g of y, that's that curve. This is y equals d, this is y equals c. Okay, so we're looking at this region here, and so let's say you separate this into subintervals, and so you take this subinterval, so then that's the height of that point there, and the height of that point there, so you have a rectangle here. So the approximating rectangles are now horizontal, right? So we were approximating areas with vertical rectangles before. You could approximate an area with horizontal rectangles. So here, the height of the rectangles are a difference of x values, and height is a difference of y values. I mean, the width is a difference of y values. So these are horizontal rectangles, and you're approximating an area with horizontal rectangles. Okay? And the actual area is determined by an integral